Hi, and welcome back to Codex. Our talks this summer feature graduate students and postdocs who were nominated to speak by their senior colleagues. Today we have Shuang Guan, who is currently a student at Tufts and is about to start a postdoc at Georgia Tech. Shuang will tell us why HRT is true for real functions and 4 points. Take it away, Shuang.
All right. Thank you everyone for joining my talk. First, I want to thank the organizer for holding this postdoc and graduate student summer session, and thanks to Emily for setting up the schedule. And thanks to John for listening to my practice talk, and Joy for helping me organize these slides. All right, so and also I want to thank my PhD advisor, Professor Okoudjou. Without him, this wouldn't be possible. All right, so this talk is about well-known conjecture in the time frequency analysis. And today I'm going to tell you that the HRT conjecture is true for real functions and in arbitrary 4 points. All right, so this talk is mainly divided into three sections. So the first part is about I'll introduce what's the background of the conjecture, what's known about it, something like background stuff. And the second part is about our contribution. And the third part is I want to quickly sketch why our technique here doesn't generalize so well to further like more ambitious results. For example, for whether the HRT is true for arbitrary 4 points and arbitrary functions. Right? All right, so let's first give a motivation about the HRT conjecture. So what do we mean by HRT conjecture, right? So there's a well-known metaphor that first you consider on the top left, you have an original piece of music. And something you can do about it is you can shift your music with some time, or you can play it in a different pitch. And the conjecture refers that whether the same song, if you shift it in time and different pitch, and then you combine all the shifted and the pitched version of it together, is it possible that you got complete silence? I mean, of course, during the shift and pitch, you are not going to make it trivial. So there are some weights on uh, each each operations you do it, but whether non-trivial like operations can give you complete silence. That's a classical metaphor about the HRT conjecture. All right, so then I'm gonna introduce some basic notations in time frequency analysis. All right, so for example, given a signal G, which is, let's just assume is L2 integrable in real line. It can be a sound, it can be, for example, a signal. And something you can do about it is you can translate it by a parameter A. So you just do a translation in your X here, in your time domain maybe. And something else you can do here is consider a modulation, which is you multiply a factor of e to the 2 pi I bx in front of it. So here I gave a graph of those two operations. So translation is just you shift it in the x-axis, right? And modulation is a little bit hard to show. I only give the real part here, and which is you multiply it by like a trait polynomial here, and you can see that it's like you pitch the signal in different frequencies. And as it's well known that those two operations are like commute under Fourier transform. Well, not really commute, but there's some relation under Fourier transform. So, all right, next thing is I will introduce what is HRT conjecture. So given a signal, given a function G in L2 of R and some finite set lambda, subset of the R2, you can define the associated Gabor system, which is the which composed of the translation and modulation of the original function G, and you just consider the collection of such functions. And the conjecture proposed by Hayal, Ramanathan, and Topiwala asserts that for a non-trivial function g and the arbitrary set lambda, the Gabor system I introduced above is linearly independent. So specifically, this linear independence means that if I'm given some AK and BK and the function g, and consider the summation of those modulation and translation with some coefficients and set it equal to 0, this would means that all the coefficients, the ci in front of it, are all 0. So that's like the linear independence definition from linear algebra. And this conjecture is posed in 1999 and is still open after nearly 30 years. So it's been, oh, it's not nearly actually, it's exactly 30 years now. So let's introduce why it is considered a hard problem. So because all the existing results are relying on some extra structure, which the function g and the lambda don't necessarily have. So for example, there's some tools to use function theories to prove some partial results, but to do that, we need to require some specific function g, right? Because the g is in L2 is quite general. It has so many functions here. And for some specific lambda, there's ways to prove a partial result using von Neumann algebras, but still the lambda requirement is that it's only a subset of R2, which is also a general assumption. So therefore, the main reason why it's hard because no single perspective can cover all the general cases. So so let's now introduce some known results, and I will sketch a short proof about one of it. So first thing is for arbitrary lambda and the support of G is compact, then we know the HRT conjecture is true. And by the way, remember the music like metaphor I introduced at the first page. So it's like in real life, all the music are finite lengths that there's no music that's like has infinite lengths. So by compact here, it's like a length of the music is finite, but when you consider the infinite length music, the problem becomes much harder, right? But at least we know that whenever the support of G is compact and the lambda can be anything, then we know the conjecture is true. So there's some good news here. And on the right-hand side, I have a figure about the support of G is in some AB. It's just a, well, compactly supported function. And something else we know is that whenever for arbitrary lambda and G Gaussian, so something like bell curve, you can see that as some more relaxed condition about compactness, but still some restriction on the type of function here, right? And I should mention that Gaussian can be extended to all the Hermite polynomials. So you can multiply polynomial in front of your Gaussian and still get positive results. And the third thing is whenever your lambda falls under a lattice and the G is arbitrary function, that's proved by Professor Linnell in 1999. And the fourth result I have here is also in the original paper of the HRT conjecture. It says that for arbitrary 3 points, you can draw 3 points wherever you want and consider any function, you know, the conjecture holds true. And then I'll introduce that whenever the points lying on a 2-2 configurations, so by 2-2 configuration, I mean that 2 points lying on one line and other 2 points lying on a parallel line. So you can see from the figure, and this is some good results in 2012. And something else we know is that for any G and almost every 1-3 configuration, where by 1-3 I mean that one point lying offline and three others lying on another parallel line. Oh, there's a three other point lying on one line, so there's no parallelness here. And by almost everywhere, I mean, I'll skip the detail, but you can see that you can just believe that this is almost done here. And in short, the conjecture is open for general G and arbitrary 4 points lambda. And let's now introduce, get some flavor on how the proof of those things work. So let's say some warm up. So let's consider what if we only have modulations and there's no translation at all. So you can take lambda equals to 0b1 all the way up to 0bn, where the first entry in our coordinate is always 0, meaning that there's only modulation here, there's no translation here. And we assume it's linearly dependent, so we just set this equation to 0 and see if there's any contradiction arising from here. And on the set where g of t is non-zero, we can divide both sides by g of t, right? Because it's non-zero. Then we get the linear combination of those exponentials is 0, but notice that distinct exponentials are always independent, where the functions e to the 2 pi bi t with distinct bi are linearly independent, which forces all the coefficients here to be 0. Therefore, our original equation here can hold true unless all the ck are 0, right? So this tells you if there's only modulation, the HRT conjecture is always true. And with that result, we can actually prove quickly why the compact supported G gives positive result on the HRT conjecture. So let's say, suppose we have support of G is in some interval CD, and you have the linear combinations is 0. And you can look at the leftmost translate, right? So, I mean, there are several translates, several modulations, but always you can pick up the leftmost one. And near the left edge, I mean, you can see that on the dashed line here, only that part is non-zero. So therefore, this tells you that that coefficient here must be 0. And although the modulations might mess up with a little bit, we just prove that if it's purely modulation, it's always linearly independent. So therefore, we can conclude that for the labeled first function here, that coefficient is always 0, and we can repeat this process. And this will tell us that all the coefficients ck here must be all 0. And I mean, it's not a very rigorous proof here, but at least you get a flavor of the question. And you can imagine that the compactly supported G gives us positive results. All right. Now let's see. Also, something interesting here about the Gabor system linear independence is that the metaplectic transforms preserve linear independence. So by metaplectic transform, I mean the symplectic maps and the translations. So it's like given arbitrary 4 points, it's hard to deal with, right? But you can do something about it. You can shift it. You can, for example, rotate it. You can take a reflection to make it more seems regularized. And 4-point problem is something we are interested here. So let's see how we deal with arbitrary 4 points here. So, I mean, just dots 4 random points. And let's first take a look at the blue one. So we can always shift it to 0, 0 because, well, the metaplectic transform preserve linear independence as suggested by the title. So we can always translate the first one to 0, 0. And we can do some rotation to rotate the orange one to 0, 1. And then we can do some shear operation to make the green point to S0, where well, we can assume x and 1 are, we can assume the distance between like the orange point and green point are the same, right? So we can just assume the orange point takes 0, 1, and the green point takes as 0. So, and the fourth one, we just don't do anything about it. It's free. So therefore, we can safely assume that whenever we consider a 4-point problem, we can consider our lambda is it's like 0, 0, 0, 1, S0, and AB, where S, A, and B are some free variables. Right. All right. So something we can do once we have like 0, 0, 0, 1, S0, and AB is that we can take something further. So for example, if we consider a reflection of points, we can reflect 0, 1 to 0, -1, and we can reflect AB to A minus B, right? And therefore, notice that the point at S0 doesn't change if you take reflection. And whenever your function g is real, the translation of g is equal to the conjugate of translation of g, right? Because it's real. And you take the conjugate of the real function, it doesn't change. Although this doesn't hold true for the non-trivial frequency modulation there, because remember that e to the 2 pi I, well, something x is complex valued, as I showed at the second slide. So therefore, as a consequence, if we can prove HRT for all 3-2 like symmetric configurations like this, then we know that HRT for all 4 points with real valued function g is true. And that's what we are going to do here is we are going to prove the HRT for all 3-2 configurations with symmetric setting like this. All right, so let's proceed. And now let's introduce the 3-2 configuration here. And so let's fix some d. And again, by the mathematic transform, we can somehow normalize our translation parameter here, right? So we can now assume our 5 points takes the form 0, 1 over a, 0, 0, 0 minus 1 over a. Sorry for the typo here. And 1AB and 1 minus AB. So those are the 5 points we are going to consider, and we are going to consider the HRT conjecture under this lambda here. So, and in 2019, Professor Okoudjou proposed this method, and he proved some result here. And in our work here, we prove all the remaining cases, and together with all the remaining cases, we prove the HRT for all symmetric 3-2 configurations. And this leads to the result from the title that HRT for arbitrary 4 points with real valued functions is true. All right. So is there any questions so far, maybe? All right, so now I'll move on to specifically our contributions here. So, so for case 1, we suppose our parameter b here is some rational is a rational number. So therefore, we can write it down as lambda is 0, 0, 0 plus or minus 1, and a plus or minus b. And it turns out this case is easier than we thought. So if we consider a equals to a matrix like this, it's like a element of the symplectic group. Therefore, if you apply the translation, apply this a on those points, we can make our lambda falling under the lattice. Therefore, the case 1 here is solved straightforwardly. We call that so case 1 here is whenever the parameter b here is rational. All right. So let's now recall the 3 cases. We just quickly show that the case 1 is true. And the remaining cases are whenever AB is in rational number, the product of AB is in rational number, and in case 3 is that AB and product of AB doesn't have any rationality whatsoever. And now we can move on to case 2 because so all right, let's recall what we have here. So lambda is 0, 0, 0 plus or minus 1 over a, and 1 plus or minus ab. Those are 5 points of lambda. And we suppose the Gabor system composed of arbitrary function g, and lambda is linearly dependent. So we prove this by contradiction. And we can write down the equation here, right? So C1, G of t corresponding to the point 0, 0. You can see that G of t here doesn't have any translation, doesn't have any modulation, it's just itself. And C2 times e to the 2 pi I over at, and times G of t corresponding to the element 0 and 1 over a. It is a function itself and times the modulation by 1 over a. And C3, well, it's just 0 and minus 1 over a here. So those are 3 points you can see lying on the no translation side. And C4 is e to the 2 pi I AB times G of t minus 1 corresponding to the point 1 AB here. So you can say it's translation of G by 1 times the modulation with a factor of AB plus some weight, some constant C5 times e to the minus 2 pi I AB times G of t minus 1. And this point corresponding to translation by 1 and modulation with minus AB. And we set it to 0, which is an essential step for like linear independence, right? And we are going to try to see if there's anything wrong with it. So we are going to try to see that unless all the coefficients here are all 0, this equation cannot hold. All right, so let's see. We can first thing we can do is we can do some grouping. So we can combine anything about g of t and set it equal to something about g of t minus 1, right? I didn't do anything here other than remove the red parts to the right-hand side. And we are going to call the function c1 plus c2 e to the 2 pi I over at plus C3 minus e to the 2 minus e to the e to the minus 2 pi I over at as P of t, and I'm going to call Q of t as C4 e to the 2 pi I ABT minus C5 e to the minus 2 pi I ABT. Okay, so I just defined two trig polynomials here as P of t and Q of t, and to make sure my notation looks clearer in next few slides. All right, so once we have that, we can obtain something we just call it a fundamental equation here. So we have the absolute value of g of t times absolute value of p of t is equal to the absolute value of g of t minus 1 times absolute value of q of t. And because our assumption about g is only in L2, the function itself is only defined almost everywhere. Therefore, this equation can only hold almost everywhere for t in real numbers. Right, so this all boils down to the equation here, right? And as you can see, right, there's some like recurrence structure here, right? Something about g of t and something about g of t minus 1. And we're going to try to explore what's interesting about it. What can we obtain from there? All right, so now we can fix t of 0. We can just fix a t of 0 in the support of g. And as it further goes, I may impose some further restriction on our T0 here, but right now let's just consider our T0 is such that G of T0 absolute value is equal to the absolute value of G of T0 minus 1 times the absolute value of, well, the ratio Q of T0 and P of T0. And you can see that the reason we want our T0 here is in the support of G is that, well, if it's not in the support, then I just get 0 equals to, well, 0, which is not so interesting. So therefore, let's just assume we fix one T0 such that this one-step equation makes some sense here. And we can always find such T0, well, because B is non-trivial, right? And now we can evaluate at T equals to T plus 1. And you can see that if we plug in T0 plus 1 there, then we get G of T0 plus 1 in absolute value is equal to absolute value of G of T0 times absolute value of the, well, the quotient of two trig polynomials. And you can see that something interesting is already happening here, right? Because we don't have to assume anything about whether T0 plus 1 is in the support of G, as long as the T0 plus 1 avoids 0 of P and Q, right? Because as long as G of T0 is non-zero, G of T0 plus 1 would also be non-zero if it avoids, if the T0 plus 1 avoids 0 of the trig polynomials. And because the trig polynomials always have like isolated 0, this is doable. And we can play with it a little bit because we already know what is absolute value of G of T0. In the one step, we can just do a plug-in here. And then I know that I can express G of T0 plus 1 in absolute value is equal to the absolute value of G of T0 minus 1 times these two trig polynomials. And each of it is shifted like by 1 here, right? And as you can imagine, I can do this forever. And after n steps, I can get something about G of T0 plus n here in absolute value, which can be expressed as, well, absolute value of G of T0 minus 1 times an infinite quotient of trig polynomials. And now we can do some interesting like real analysis stuff here. So because our function G is in L2, we can always find some small t0 such that if we shift the G of T0 to arbitrary n, right? So we can consider the absolute value of G of T0 plus n. As n goes to infinity, we can assume that G of T0 plus n in absolute value sense goes to 0. And I should point out that this first bullet point here, this statement is not true for arbitrary T0 in the support of G. Well, if you can remember in like real analysis, you can construct like a small triangle infinitely far, right? Which makes this statement false. But well, I'm just fixing one T0 and I further restrict some property on it. So I can just say that we can find the T0 such that when we shift the T0 infinite far, the function G of T0 plus n just goes to 0. And something else we can assume about our interesting T0 here is that we can assume that all iterations of T0 plus J, well, we can assume it avoids 0 of P and Q because of the reason that P and Q are just trig polynomials and they only have isolated zeros. So all the T0 plus J, we can assume it avoids 0 of P and Q. And those two bullet points are doable. So I get something non-trivial after n step. I mean, if T0 plus J doesn't avoid 0, I get some 0 equals to 0, something like that, right? Which is not that interesting anymore. All right, so I'm just saying that I did this for n step and it should work well, and we can prove that it worked well. All right, next thing is we consider specifically case 2 now. So recall that for case 2, we consider the AB parameter is rational, where we can assume that AB is equal to some P over Q, where PQ are integers. So therefore, the polynomial Q here is is small q periodic. And now we can pick our big N to be some number K times Q. And we keep everything about the forward iteration here, and we got something about the absolute value of G of T0 plus KQ. And because of the Q periodicity, the big Q products can split into K equal periods. And something I didn't mention, but I hope you can believe, is that, well, the iteration here I mentioned, I just did it from G of T0 to G of T0 plus 1. I can also do it for G of T0 minus 1, right? So, and that I can call it like the backward iteration, and it takes something in similar format. So by backward iteration, I can obtain something about the absolute value of GT0 minus KQ, and I can write down similarly as the forward iteration. And again, by the small q periodicity, the polynomial big Q product in the denominator satisfies this relation here. And you can see that there's some interesting cancellation already going on, right? But let me see how it works. So now I can multiply the forward and backward, like 2 iterations. On the left-hand side is just G of T0 plus KQ and times G of T0 minus KQ, which is exactly here. And on the right-hand side, I get 2 initial terms of G of T0 minus 1 and G of T0. And now I get something about purely Q ratio and purely P ratio. And because of the fact that AB is like periodic in integer, the Q ratio, there's some cancellation going on there. And the P ratio, right now, let's just assume it's bounded and harmless, right? So the Q ratio, the K dependent factors will cancel, like this slide, like the previous slide shows, and it only keeps the initial the QT0 square, and this would be independent of K. And then therefore, since the iterations of T0 avoids 0 of P and Q, so the P ratio, it avoids all 0 of P as well, is just remain bounded. Therefore, the left-hand side is bigger than or equal to some constant, where the constant is composed of some initial terms, right? Like the QT square, QT0 square, and G of T0 minus 1, G of T0, which is strictly positive because of our assumption that T0 avoids 0 of Q, right? But on the left-hand side, I just mentioned that I can make sure the shift of T0 infinitely far just goes to 0, all right? Therefore, the left-hand side just go to 0. The right-hand side, I have something positive, which is a contradiction.
I think Matt has a question.
Yes, yes.
Sorry, I thought I was muted. Sorry. Hi. Did you mention why we need to take absolute values of all of these expressions?
Oh, well, I just want to make sure that, for example, to make it more consistent, right? Because at somewhere I just want to avoid all the first. Maybe one of the reasons is to avoid the sign issue here. I mean, I can just take absolute value and make it clearer, make it it looks more clear. Yeah. And during the proof, there's some proof that shows that something is strictly bigger than 0, which would make it
Okay.
nicer. Yeah.
Okay.
And
Thank
you can see that on the left box equation, the left-hand side strictly goes to 0, but the middle term here is positive. Therefore, that's a contradiction here.
Okay, that makes sense. Thanks.
Thank you. All right, so this is the contradiction I need for our case 2, and I guess now we can move on to case 3. And recall that our configuration here is 0, 0, 0 plus or minus 1 over a, and 1 plus or minus ab. And I just solved case 1 and 2. Now the case 3 is the hardest case, and I'll now try to illustrate why it's also true. So, but first, let's see how much is carried over from case 2 about case 3. So recall that our Q of t, well, it's just a trig polynomial like this. But now our AB product is not rational anymore. So as a trig polynomials, we can do some normalization and so suppose that the absolute value of Q of t is between 0 and 1, right? And because of the periodicity, the value at t0 plus j for integer j, because it's periodic, let's suppose it starts from the leftmost blue point here. It keeps periodic, and the product would just telescope. But now, if AB is not rational, then the orbit might fill densely, right? Because, well, if we consider t varies from t0 to t plus j for integer j, the value of Q of t depends on only the fractional part of it because it's a trig polynomials, and that orbit will fill densely, and therefore it just doesn't repeat. So there's no more periodicity over rational. And the new idea is that although periodicity is gone, there's a way to find some second point T1, whose orbit is a mirror of that of T0. And I'll just say that the reason of this is that for absolute value of a complex function, you can consider its conjugate, and the absolute value doesn't change, right? So therefore, you can find some different points that's somehow like the mirror of it if we draw a picture. And they take the same absolute value, and there are different points to start with, but if we iterate it, they are the same value. And I'll try to illustrate it as far as I can. So let's see. So suppose the absolute value of Q takes the same value as the points that are mirror image about 1 over 2. So let's say our T0 starting with the leftmost point, and T0 plus J as J from 1 to N. Well, let's just assume that it takes value all the blue points there between 0 and 1. I use 4 points, 4 iterations. And the interesting thing is that I can always find some T1, which is like the same distance to the central point 1 over 2 with T0, such that Q of T0 and Q of T1 is the same value, and Q of T0 plus 1 is the same value of Q of T1 minus 1. And as you can see, like the leftmost T0 matches the value of T1, and the second one matched the third one on the bottom. The third one matched the second one, and the fourth one matches the first one. So therefore, I'm just claiming that there's a clever way to find the T1 such that the backward steps of T1 exactly matches the forward steps of T0. And that's from the fact that the conjugate of the function and itself takes the same absolute value. And because of the trig polynomial, because of the density of the orbit for the irrational number, we can always find such T1 and we can do the similar product match and we can get a similar contradiction as previous steps. So, well, let's just assume we did that, and we can multiply the orbit of the T0 from forward and the orbit of T1 from backward. So left-hand side is like the shift from T0 to the positive big N, and the right-hand side is shift from T1 to the negative big N. And the capital K here denotes the cancellation of Q product. Well, there's some harmless reminder for big Q, because we assume our T0 and T1 and its shifts avoid 0 of Q. We can assume that big K here is just something harmless. And there's also some other members who are harmless. It's the absolute value of GT0 minus 1 and the absolute value of GT1, which are chosen similar as we take T0, but we assume that T1 has some mirroring property. And as similar as above, the left-hand side is just you shift T0 and T1 infinitely far, therefore individually they go to 0. And the right-hand side, there's some non-zero constant. And because also the P here, well, P, we picked T1 and T0 avoiding their zeros. And not right now, we can assume those P products are harmless. So therefore, we can derive some similar contradiction. And that's basically the spirit of the proof of how we did it. All right. Now let's see that why our technique doesn't generalize so well. And recall that in our proof, I deliberately avoid to study about P here. Right? The P here consists of those three components. Each of the three components has frequency minus A, 0, and A. And they are all multiples of one irrational number, which is just A. And this is something specific about the symmetric 3-2 configurations. And if we want to do something further, if we want to drop off the symmetric conditions here, and what happens if the frequencies are less structured, right? Does it keeps harmless as before? Well, let's see. So let's drop the symmetry, and then we have a general 3-2 configuration, which is like, instead of like all the symmetry there, I just have those like the distance between alpha I and the distance between alpha 3 and alpha 2 and alpha 1, alpha 2 are distinct. And therefore, our big P of T is in this format. Instead of previously, they're all A or minus A, right? They are just A and minus A. Right now, I will have their distance would be distinct between alpha 1, alpha 2, and alpha 2, alpha 3. And this turns out to make the problem harder. So you can see that for symmetric case, if we consider the independent irrational A, then the P of T, if we consider the orbits, if we consider T0 plus K, then essentially the value of PT depends on AN mod 1, right? Because it's a trig polynomial after normalization. Therefore, if we consider N goes big, the orbit, like AN mod 1 here, is just a circle. And for the circle, we can handle it pretty well. But if we consider asymmetric case, our PT takes those more difficult form, then turns out that the orbit of alpha 2n and alpha 3n mod 1 is a torus. And that would make the problem much worse. So if we look back, the product here, the P product here, if its orbit is always a circle, this quotient, we can show that we can handle it well. But if it's under a torus, there are many uncertainty things can happen, and well, it's just possible that this infinite quotient here can be zero, maybe. So that's like a difficulty if we want to move further from what we have here. And I think that's all for today. And this is a picture my wife took in Save a Fox Rescue in Minnesota. And I just think it's very cute. Yeah, thank you.
All right. Let's thank our speaker by clicking buttons. That's what Dustin always says. And you can shut off the recording, Michael.